All right, let's get right into it. We're going to break down the really cool physics behind how a huge airplane flying miles up in the air knows exactly how fast it's going.
I mean, think about it for a second. It's a pretty interesting problem, right? When you're way up there, there are no street signs, no landmarks, nothing. So how in the world does a pilot get that super important speed reading? Well, the answer is incredibly clever, and it's all about understanding the air. And here it is. This is the hero of our story, the pitot-static tube. I know, it doesn't look like much, does it? But this little thing is an absolute masterpiece of engineering. This is the sensor that solves the whole puzzle. And the best part? It does it with pure fundamental physics, no crazy electronics needed.
And that's what's so beautiful about it. To figure out how this thing works, you don't need a PhD in quantum physics. Nope. We just need to get a handle on two basic laws that explain how fluids, like the air, move around. So let's break them down.
Okay, section 1. First things first, we've got to talk about a fundamental rule of how things, well, flow. And this isn't just about airplanes. We're talking water in a pipe, blood in your veins, you name it. It all boils down to one word: conservation.
And here's the big one, the law of conservation of mass. Now, for what we're doing, it's actually super simple. It just means that what goes in must come out. You can't just create or destroy stuff. So if you push a bunch of air into one end of a tube, that exact same amount of air has to come out the other side. Simple as that. Mass is conserved. And this right here, this is just the math way of saying that. It's called the continuity equation. All it means is that the area of the tube multiplied by how fast the stuff is moving, the velocity, at one spot has to equal the area times the velocity at any other spot down the line. It's a balancing act. So here's the really important takeaway. If you squeeze that tube, right, you make the area smaller. Well, the air has to speed up to get the same amount through. You've all done this. It's like putting your thumb over the end of a garden hose. The area gets smaller, and whoosh, the water shoots out way faster. It is the exact same idea. Okay, let's put some real numbers to this. Imagine air flowing into a nozzle at 10 meters per second. Then the nozzle gets narrower. To keep everything balanced, that air has to just take off. It accelerates like crazy and comes out the other side at 62.5 meters per second. That's a huge jump in speed from just a small change in area. Just hang on to that idea because it's super important. All right, so changing the area changes the speed. Got it. But an airplane isn't flying through a tube, right? You can't measure the area of the sky. So how does it measure its speed? Well, this is where the magic happens. The secret is linking that speed to something we can measure really easily: pressure. And that brings us to our second big law. And honestly, this one is a total game changer. It's Bernoulli's principle. And if you remember one thing, remember this: faster moving air has lower pressure. Slower moving air has higher pressure. That's it. This backward relationship is the absolute key to everything. It's all about conservation of energy, but for fluids. Now, to really wrap your head around this, let's break down pressure into two types. First, you've got static pressure. Think of this as the background pressure of the air just being there. It's pushing on you from all sides right now. Then you have dynamic pressure. This is the pressure that comes from the air moving. It's the energy of its motion. So Bernoulli's principle is all about the trade-off between these two. Okay, now imagine the air is flowing along, and then bam, it hits a wall and is forced to a complete stop. We call that a stagnation point. At that exact point, its velocity is zero. So what happens to all that energy of motion, that dynamic pressure? It can't just disappear. It gets converted back into static pressure, which means right at that spot, you get the highest possible pressure reading. So you can basically say this: total pressure is just the background static pressure plus the dynamic pressure from its movement. And the pitot tube? It's just a brilliantly simple device designed to measure two of these things so we can figure out the third one. And here's how it does it. So, that little hole right on the front, it faces directly into the wind, creating that stagnation point we just talked about. That measures the total pressure. Then you see those little holes on the side? Those are the static ports. They're not facing the wind, so they just measure the regular background static pressure. The plane's computer then does one simple thing. It subtracts the static pressure from the total pressure. And what's left over? That's our dynamic pressure. And since we know dynamic pressure is caused by speed, we can work backward and calculate the plane's airspeed. It's so simple, so elegant, and it just works.
Okay, so in a perfect world, that's the whole story. Measure two pressures, do some simple math, and boom, you have your speed. But you knew there was a but, right? As any pilot or engineer will tell you, the real world is messy. And the air itself, well, it changes. And here's the catch. That simple math equation we use to get speed from pressure, it relies on one other thing, air density. But air density is not a constant. The higher up you fly, the thinner the air gets. Plus, when you go really, really fast, the air starts to compress. Both of these things throw the calculation off and introduce errors.
So how do we deal with this? Well, pilots actually use a whole family of airspeeds, where each one is a more corrected, more accurate version of the last. Let's just walk through them. It starts with indicated airspeed, or IAS. That's just the raw number the gauge shows you, based on that pressure difference. Then we correct for little errors in the instrument itself, and that gives us calibrated airspeed, or CAS. Next, we account for the air compressing at high speeds to get equivalent airspeed, EAS. And finally, the last and most important step, we correct for the fact that the air is thinner at altitude. That gives us our true airspeed, or TAS. That is how fast the plane is actually moving through the air mass. It's like peeling an onion to get to the true number at the center.
And you know what's really cool? These same basic ideas, conserving mass, conserving energy, Bernoulli's principle, they don't just tell us how fast a plane is going, they explain so many other things. We're talking about how a wing generates lift, why a race car sticks to the track, and even how a soccer player can bend a kick. Let's take something called the boundary layer. Air is a little bit sticky, right? It has friction. So the air molecules right up against a wing's surface kind of cling to it. This creates this incredibly thin layer of air that's moving much slower than the rest of the flow. And this tiny little layer has a massive effect on both lift and drag. And inside that layer, the flow can go one of two ways. It can be super smooth and orderly, we call that laminar flow, or it can be messy and chaotic, that's turbulent flow. Now, you'd think turbulent is always bad, but it actually has more energy, and sometimes that's a good thing. It can help the airflow stick to the wing better at high angles and help prevent a stall. Okay, now for a really fun one, let's take all this physics and apply it to sports. You've probably heard of the Magnus effect. When a player puts a spin on a ball, the surface of the ball actually drags a little bit of air around with it. So think about it. On one side of the ball, that spinning layer of air is moving with the wind rushing past, so the total speed is higher. But on the other side, it's spinning against the wind, so the total airspeed is lower. So, what did Bernoulli tell us? Faster air, lower pressure. So now you've got a pressure difference between the two sides of the ball. There's a lower pressure on the fast spinning side and higher pressure on the slow spinning side. And what does a pressure difference create? A force. That force pushes the ball from the high pressure side to the low pressure side, and that's what makes it curve. The famous banana kick in soccer. It's not magic, it's just Bernoulli's principle. The very same physics that tells a 747 its speed. So the big takeaway here is that these aren't just some dusty equations in a textbook. They are the invisible rules that are running the show anytime something moves through the air or water. I mean, if the exact same principles can explain how a massive jumbo jet measures its speed and how a soccer ball can curve into the goal, it really makes you wonder, doesn't it? What other amazing invisible forces are shaping our world right now, just waiting for us to notice?